Welcome to this explainer. The history of science is absolutely packed with brilliant discoveries. But I've got to say, very few have an irony quite as profound as this one. Albert Einstein, pretty much the ultimate architect of our universe, created a theory so beautiful and precise that it completely rewrote our understanding of reality. But hiding deep inside his own elegant equations was a terrifying mathematical monster. A monster so illogical, so incredibly destructive, that Einstein literally refused to believe it could exist. So today we're going to explore exactly how this mathematical anomaly went from a totally dismissed error to one of the absolute most frightening physical realities in our entire universe. Okay, let's actually dive right into this by looking at a single, incredibly simple thought experiment that managed to dismantle 2.5 centuries of scientific consensus. Picture this. It's 1907, and Einstein is just sitting at his desk in a patent office in Bern, Switzerland. Suddenly, he realizes something. If a person is in free fall, their weight effectively disappears. He understood something really profound that literally everyone else had missed. Gravity has this unique property of disappearing as a result of its own effect. This one simple, kind of bizarre realization, that a falling person wouldn't feel gravity, became the lighthouse in the dark that guided him to completely rethink how the whole universe works. Section 1. Rethinking Space and Time. Now, before things get too complicated, we really need to ground ourselves in exactly how Einstein changed the rules of the game. And to really grasp his genius here, we have to contrast it with what came before. For 250 years, Isaac Newton's universe was the absolute law. Newton viewed space as this rigid, straight stage, and time as a giant universal clock ticking away identically for everyone, everywhere. Gravity? Well, that was just some mysterious, invisible pull between objects. But Einstein? He threw all of that right out the window. He proposed that space and time are not separate things at all. Instead, they're intimately connected into a four-dimensional geometry called spacetime. And time absolutely does not tick the same everywhere. Each region of the universe, each galaxy, actually has its own time. To really picture how this works, imagine space-time as a giant, flexible block of jelly. Seriously, just picture a huge block of Jell-O. When you place a super heavy object into it, like a star or a planet, it totally distorts and curves that jelly. So the planets aren't being invisibly pulled by the sun, they are simply following the natural curves created by the sun's massive weight sagging in the fabric of space-time. Gravity isn't a pull at all. It's really just the geometry of the universe reacting to matter. Section 2. Proving the new universe. Of course, having this beautiful, elegant vision in your head is one thing, but proving it mathematically, that is an entirely different beast. Let's walk through this incredibly rapid progression. After his epiphany in 1907, Einstein moved to Zurich in 1912. The mathematical obstacles were basically insurmountable, so he brought in his brilliant mathematician friend Marcel Grossmann. And man, they worked like absolute monomaniacs. Finally, in 1915, after 8 grueling years, Einstein formulated his single, elegant equation. It perfectly predicted the peculiar shift in the orbit of the planet Mercury, which was this glaring flaw in Newton's theory that no one had ever been able to crack. But the real clincher? That came in 1919. A British astrophysicist named Eddington traveled to an island off the coast of Africa during a total solar eclipse. He photographed distant stars and proved, without a doubt, that their light was physically bending around the curved spacetime of our sun, exactly as Einstein predicted. This one observation made Einstein an overnight global superstar. Section 3. The Mathematical Monster. But here is where the story takes a dark turn. Just as the world was celebrating this triumphant new understanding of reality, a fatal flaw was discovered hiding deep, deep inside the math. While Einstein was finalizing his work during World War I, a German physicist named Karl Schwarzschild used Einstein's equations to calculate the distortion of space-time generated by a star. It was a titanic mathematical achievement, but it exposed a massive glitch. Actually, scratch that. It was worse than a glitch. There's this amazing story of a dramatic confrontation later in Paris, where the mathematician Jacques Hadamard stood up, pointed threateningly at Einstein, and showed him exactly what the singularity meant. At a specific radius, the math literally requires a division by 0. It results in infinity. It creates a mathematical monster, this impenetrable black bubble where space simply ceases to exist and time stops entirely. I mean, this was a total disaster. Think about it. If you send a satellite towards the sun, what happens if it hits this mathematical boundary? Does it just disintegrate? Does the universe just end right there? This terrifying edge-of-the-world mathematical breakdown caused an absolute uproar. Physicists grew extremely wary. They really didn't want to get their heads around an equation that predicted space and time just falling flat on its face. The scientific community, and yes, even Einstein himself, largely abandoned the whole concept of the singularity. They just treated it as an annoying mathematical quirk rather than actual physical reality. Now, to understand why they felt so safe just sweeping this under the rug, we have to talk about a very specific number: 3 kilometers. Calculations showed that for this terrifying singularity to actually become visible in our solar system, our entire massive sun would need to be completely crushed down into a tiny sphere just 3 kilometers across. At the time, the idea that a star could implode to that kind of extreme density was considered absolutely 100% impossible. Einstein even went so far as to write what his colleagues called one of his worst papers ever, desperately trying to prove that nature wouldn't ever behave this way. Section 4. Discovering Dead Stars. Well, as it turns out, the universe is far, far stranger than Einstein ever dared to imagine. Fast forward to the 1960s, and we start to see how the next generation resurrected his monster. The major turning point came in 1964 from a brilliant British physicist named Roger Penrose. As the story goes, Penrose was crossing a busy street in London with a colleague. The conversation paused as they dodged traffic, and in that brief, fleeting moment of silence, an unannounced idea just popped into Penrose's head. He envisioned what he called a trapped surface, proving mathematically that when a massive star runs out of nuclear fuel, gravity definitively wins. The star shrinks, its surface gravity increases, causing it to shrink even faster, until the very atoms themselves collapse. All of that matter is crushed down to a point of zero radius. Penrose basically proved that gravitational collapse to a singularity wasn't just some mathematical error. It was an inevitable, terrifying reality of physics. And there's this massive, fascinating contrast here between theoretical math on a chalkboard and the pure physical grit of actual astronomical observation. Because while the theorists were busy doing the math, a young scientist named Jocelyn Bell Burnell was out in a field, literally wielding a sledgehammer to help construct a massive radio telescope. Working out there in the freezing cold, she noticed a highly curious signal, a string of pulses about 1 1/3 seconds apart. Against massive skepticism from the establishment, she proved these signals were real. She had discovered pulsars. We now know that pulsars are neutron stars, the dead, incredibly dense remnants of massive stars. Her gritty, hands-on discovery definitively proved that extreme, dead stars really do exist out there in the dark. So the crucial takeaway here is that reality is often way scarier than fiction. Neutron stars are the closest things we have to black holes, and they pack the mass of 1 billion million tons into a ball just 10 kilometers across. And the extreme weirdness of these dead stars is a direct result of Einstein's relativity. The gravity is so immense it bends light rays entirely around the star. That means if you stood on one, you could look straight ahead and see the back of your own head over the horizon. Time slows to an absolute crawl. And if you actually tried to land on one, well, the gravitational gradient is so severe that the pull on your feet would be vastly stronger than the pull on your head. Physicists use a highly technical, totally visceral term for this: spaghettification. Your feet are pulled from your legs from your body, literally stretching you into a thin string of atoms before you even drop onto the star. Absolutely wild, right? Section 5. The Quantum Gravity Frontier. As terrifying as neutron stars are, they do still have a physical surface. But what happens if the dead star is so incredibly massive, it becomes a full-blown black hole? Let's venture into the ultimate unknown for a second. When you cross the horizon of a black hole, you enter a trap from which not even light can escape. But what happens at the very center? Well, general relativity gives us a horrifying answer. The fabric of space-time literally tears apart and ceases to exist entirely. At this singularity, Einstein's brilliant rules of the universe just completely break down. His theory simply cannot explain what happens next. To even try to figure out the inside of a black hole, we have to shift our explanator away from general relativity entirely and jump into a microscopic frontier: quantum mechanics. And let me tell you, when you mix general relativity with quantum mechanics, things get incredibly strange. Physicist Carlo Rovelli has this speculative, mind-bending theory called loop quantum gravity. He suggests that inside a black hole, the collapsing star reaches an unimaginably tiny quantum state, and then it immediately bounces out in a massive explosion. The whole thing takes just a few milliseconds. But, and here's the crazy part, because immense gravity violently slows down time, those few milliseconds inside the black hole correspond to billions and billions of years for us observing from the outside. So what we see as a static, dark, silent black hole might actually be an exploding star playing out in the most extreme slow motion imaginable. As we try to wrap our heads around these massive cosmic contradictions, it's incredibly humbling to think about this quote by Isaac Newton. Both Newton and Einstein pushed the boundaries of human knowledge further than anyone thought possible. Yet, at the very end of his life, Newton humanized this whole struggle beautifully. He said he saw himself just as a child, happily finding a few beautiful pebbles on the beach, totally aware of the immense, unexplored ocean of mystery lying right in front of him. Every single question Einstein answered only peeled back a layer to reveal a much deeper, much more profound mystery beneath. And really, that brings us to the ultimate question we're left with today. Einstein proved that time is not universal, and now quantum gravity theorists are writing incredibly complex equations where time isn't even a fundamental ingredient of the universe at all. So we're left to ponder, if time stretches, if it slows down, and perhaps even ceases to exist entirely inside a black hole, what really is the passing of time? Is it just a localized illusion? It's a question that started in a quiet patent office in 1907, and it's one that absolutely continues to haunt the greatest minds of our generation. Thank you so much for joining me on this explainer, and hey, keep questioning the universe around you.